Hi, everybody. Hey, big shout out to Matt. Thank you very much for the help setting up. Okay, good. Wouldn't have been able to do it without Matt. So what we are doing, does everyone hear me? Tell me, yeah, looks like you can. Okay, good. So welcome. Good morning. Thank you. Yeah. And this is the first time I am broadcasting live or recording. You've seen me recorded before for your ionic compounds lectures, but here we are. So welcome, thank you for your patience in this and everything, and let's see. So I wanted to show you a couple of things. I know I keep getting blurry and everything, but let me show you a couple of things online real quick. So I'm gonna share my screen with you. All right, so it turns out also that we're just going to keep the same meeting link for lab today and for open hours. So we're just going to I'm just going to stop the recording and you will be able to come back at lab time and then again at open hour time. I'm going to start the recording back at those times. So it's the same link today for lab and open hours. So let's go to modules, and I just wanted to show you where you can check your work, right, for the worksheet that we had last week that we ended with, where you were calculating the mass, right, in a chemical reaction. So here's the key right here. In week 7, that's when we did it, and it's all right here for you. Okay, so that's what we did. Remember about the rat poison and calculating the theoretical yield of the toxic gas. And then the other question was about, right, photosynthesis. And so that is where you can find the key there. So make sure that you're checking, right, your key on that, all right? And let's see. So what else did I want to show you? Oh yeah, and just a reminder, right, you're all studying for your exam, which is happening on Wednesday online now. But just as a reminder, all of that is here. We're in week 8 now, and so you've got your study guide. There's this helpful flow chart, which I haven't shown you yet, but this might be useful. An SI leader actually showed me this. I had never seen it. Right? You can see with the big red X, right, that you cannot go directly between mass and particles, either atoms or molecules, but you can, right, go from grams to moles using molar mass, right, and then over here to atoms or molecules, and you can go back the other way from atoms or molecules using Avogadro's number to moles to mass. Do you need Avogadro's number for this work here? Do we need Avogadro's number when we're just going from grams of reactant to grams of product or vice versa? Let me see what you're telling me on your message on your chat here. Let me see my chat. Let's see. Do you need Avogadro's number? No, 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 I'm getting lots of no's. Okay, good. That's fun. So many no's. Okay, that's true. All right. So now you can see me again, right? Okay, good. Hi. Okay, well, let me get in focus here. I'm supposed to go toward and then come back. Okay, good. So let's see. So let's begin with chapter 6. So we're going to talk about energy a little bit today. And energy is a cool chapter because everything involves energy. Okay, every chemical reaction involves energy. And that's because it requires energy to break bonds in the reactants on the left-hand side of an equation. And when new bonds are formed in the products, energy is released. So every chemical reaction involves energy to break a bond and releases energy when a new bond is made. Just getting my marker set up here. Okay, I need a new one. All right. But before we get to start talking more about chemical energy, let's just talk about the definition that we're going to use for energy. So in chapter 6.1, or section 6.1, ooh, that's going to be, can you see, ooh, is it reversed? Oh my gosh, that's going to be an issue. Oh my gosh, how? That's an unforeseen, it's not reversed? Okay, good, okay, good. Okay, energy. Okay, so energy is involved in everything. Everything we do, we're taking energy right now from our food and using it to do chemical reactions in the body. Energy is involved everywhere, right? Every chemical reaction, every change you think of involves energy. So the definition for energy that we're going to use is just the capacity to do work. The capacity to do work. And we can define work as a force exerted across a distance. And it turns out that the total energy of a system is equal to the potential energy plus the kinetic energy of that system. So we're going to talk about the difference between potential energy and kinetic energy. And then later we'll be applying that to chemical reactions because we are in chemistry. But first we're going to talk about some more real world applications, real world like thoughts that we can have about energy, potential and kinetic. So the kinetic energy, or rather I'll start with potential energy, that's stored energy, stored up. For example, something like water behind a dam. And when that water is released, right, through the dam and it turns a turbine to generate electricity, that is then kinetic energy. So kinetic energy is the energy of motion. So water behind a dam can then flow through the dam, right? And that energy is then transferred into ocean, into motion, right? The energy of movement. Okay, so what about something like, right, any object that's up high therefore, so the water, right, has to be suspended, like up higher than where it flows down, right, in order to generate energy, to generate electricity from stored to motion, potential to kinetic. So the same goes for any object that you hold up high, right? I have this marker here. Does it have high potential energy or kinetic energy right now? You can type in your responses if you want. right? High potential or kinetic? Yeah. Good. Seeing a lot of potential in y'all, right? So yeah, high potential energy. Okay, so if I let it go and it falls to the floor, right? Did that energy get transferred into kinetic? Did the potential get transferred to kinetic energy? Right, it did. And overall, right, the overall energy total, right, is the energy of that system. It didn't change like overall, it just got transferred between potential energy and kinetic energy. So that's what we're going to see in chemistry as well. Okay, so any object up high, the other classic one is like a ball rolling down a hill, right? That has high potential energy at the top of the hill, right? And when it rolls down the hill, that energy gets transferred into kinetic energy. And then at the end, at the bottom of the hill, right, no longer does it have kinetic energy, or rather, no longer does it have as much potential energy as it had before. So an object up high has high potential energy, and then when it gets let go, right, it gets transferred into kinetic energy. So an object falling. Another example, a good example of stored energy, right, or potential energy, is the energy in food. Right? When the potential energy that is stored in food, right, is ingested by a living thing, right, that energy gets transferred into the energy of motion, which is really the energy of being alive. Every chemical reaction in our body, every thought, every movement, every heartbeat, every process in the body requires energy, and that energy comes from food. Okay, and another example, and so those are like the everyday things that we can think about, and then now we'll talk about chemical bonds. And so in a chemical reaction, the chemical bonds of the reactants on the left-hand side of the equation hold potential energy. So chemical bonds. Store energy in those bonds. And when those chemical bonds are broken, right, new bonds can be formed, which actually release energy. And so we can say that the stored energy in the chemical bonds can be released and transferred into energy of the molecular motion. How fast molecules are vibrating depends on their temperature and the energy, the amount of kinetic energy that they have. We'll say vibrations. Okay, and it turns out that it is this molecular motion that we're talking about here that is what is related to heat. So heat, right, is the transfer of kinetic energy from an object with higher kinetic energy to an object with lower kinetic energy. So this molecular motion is related to heat. So the way that we describe heat is the transfer of kinetic energy From high to low. So when we talk about heat flowing, right, we're talking about an object that's hot, right, with more kinetic energy. So we say that, right, molecular motion is related to heat. The more molecules are vibrating, the more motion, the more kinetic energy they have, the more they're able to transfer that kinetic energy to a colder object. And that is what we call heat, the flow of the kinetic energy from those molecules vibrating in an object, right, transferring that kinetic energy to other molecules in a colder object. Right? So like you've probably noticed this, I always think of this when my hand is like warmer than like my foot, right? And if you touch your foot, which direction is the kinetic energy flowing? Are the molecules vibrating faster in your hand or in your foot? If your hand is hot and your foot is cold, you can tell me. So is there a greater kinetic energy, right, greater molecular motion in your hand or your foot if your hand is hotter? Good, good. I'm seeing a lot of people say hand, that's true. And so when you feel your foot and your foot is cold, right, which direction is the kinetic energy flowing? Is it flowing into your foot, right, or into your hand? Right, you're kind of, yep, cool. Yep, your foot is cold. Your foot is cold and your hand is hot. Yeah, so the kinetic energy, right, is flowing from your hand into your foot. So every time, and my feet are cold right now, so yeah, that would feel really good, right? So anytime you touch something that's cold, kinetic energy is leaving your hand, which is kind of cool to think about, right? If you touch something that's warm, if you touch a warm cup of tea, which direction is the kinetic energy flowing, into your hand or into the cup of tea? Good. Good. Yeah. Lovely. Okay, great. Yeah, that's true. Good. So thinking about that is kind of cool. I think about it all the time. I love it. So, all right. You can maybe think about that too. All right. So let's see. And what else do I want to write here? Yeah. And it turns out that it's kinetic energy. So it's this molecular motion, right? This kinetic energy that is proportional to temperature. Okay, so the greater the kinetic energy in an object, right? We'll say proportional, so I'm not going to say equals, we're going to use a little proportional symbol. That means proportional, right? So the greater the kinetic energy, the higher the temperature. And that is how we think like on that molecular, on that atomic scale. The more atoms and molecules are vibrating in a substance, the more kinetic energy they have, and the more, right, if you're taking a temperature, you can think of it this way, if you're using a thermometer, I mean, right, the hotter the substance, the greater kinetic energy of those, say you're measuring the temperature of water, right, and you're going up from, room temperature up to boiling, and you have your thermometer in there, and what's happening is you're providing more heat to that water, right, that's the flow of kinetic energy. So the heat comes from whatever you're heating it with, right? From the heating element, gas or electric or whatever, right? That kinetic energy from the heating element is being transferred into the water molecules in your cup or whatever, right? Those water molecules have greater kinetic energy, right? And then the thermometer that you put in that cup, that kinetic energy is being transferred into the alcohol or the mercury of that thermometer. So now the thermometer, those molecules in the thermometer, right, are increasing their kinetic energy. And the more they're moving, the more they expand. And so you see on that thermometer, right, we're talking like old school, not a digital one, but old school, right? You see that alcohol or the mercury rise. And so when molecules also increase their kinetic energy, they're increasing their molecular motion, and they're able to expand, therefore, and that's why we see that rise on the thermometer. Questions so far? What questions do you have? And can everyone see everyone's comments? It looks like, yeah, okay. You don't all have to tell me. It's okay, I get it. I see it, okay, good. And can you, what questions do you have? Any thoughts like that are coming to mind? Do you want us to okay, question, what, do you want us to unmute or type all answers? Oh, unmute, oh, and then wait, will I only hear you? Or will everyone hear you, I wonder? Everyone will? I don't, oh, like if you have a question, we can try, sure, like you can, I don't know, but then I have to, I don't know. Let's just do the typing for now, I'll figure it out. But hold on, we have some questions. Okay, so is friction a kinetic energy? Is friction kinetic energy? That's a good question, let me think. I would say that friction like is a medium for transferring kinetic energy, if that makes sense. Like when you rub your hands together, right, that's creating friction, and that motion of your hands, right, is providing molecular motion to the molecules in your skin, right? Excuse me. Which is making the molecules vibrate faster and move faster. And so that means then the kinetic energy is increasing, so the temperature is increasing. So, like I said, I think that friction provides a medium to transfer kinetic energy. That's like my best answer. Does that help? Does that make sense? Let's see, so. Oh, good. So people are saying it could cause lag. Okay, cool. When does friction become potential energy? I don't know if friction becomes potential energy. That's a good question. The thing is that this is like a lot of physics stuff, right? So I'm not the, like, you know, I'm chemistry, so like the physics stuff when we're talking about like friction and all that, I'm not like the best at answering those questions, but I can find out for you. Let me see. Hold on, I'm trying to get it to focus again. Okay, there we go. A little better, kind of. All right. I'm not sure about the answer to that question about if friction becomes potential energy, but I can find out. And then here, okay, yes, the physical action causes the energy as a byproduct. Okay, good. You already have that question. All right. Okay, anything else for right now? Hey, Zaruba. Colleague. All right. So what about the growth of potential, and I mean of kinetic energy? What do you mean the growth? when you're talking about, yeah, rolling down a hill. So that, you mean like the transfer? Yeah, so the transfer of, so the energy is getting transferred from potential to kinetic when a ball rolls down the hill. That's true. Right? So what do you mean? Like, what's your question there? Does the energy transfer to, yes, it does. Good question. So yeah, like when, okay, I'm just trying to get it to focus. When you say drop this marker, right? And it has high potential energy here, right? And then you let it go, and it turns into kinetic energy, and all of a sudden it stops, right? Where does that energy go? So actually that kinetic energy gets transferred into the floor, and if you were able to measure the motion, right, the kinetic energy of the particles in the floor and those molecules, it would have increased. So by definition, therefore, the temperature would have increased a little bit, right, of the part of the floor where that marker fell into, because that kinetic energy gets transferred into the floor once it gets stopped. Does that help? Okay, good. Okay, it was still blurry here, but okay, so let's move on, and is everyone good here? Tell me if you want me to keep it up for another minute. Okay. Then let's see. Let me know when you're ready, if you don't mind. Thank you. Okay, Whitney, you're still here. Did you think you got kicked out? I'm glad you're not kicked out. Okay, okay. Okie dokie. So speaking of chemical reactions now, so we'll talk about what happens when a chemical reaction occurs, and what we need to do that is talk about the system and the surroundings. So energy flows, right, between the system and the surroundings of any process, like any of the processes that we were just talking about, specifically though for chemical reactions. So releasing heat or absorbing heat is what we're going to title this. Releasing versus absorbing heat. Which, remember, is just the transfer of kinetic energy. I'm going to try to have a rule. I'm going to draw one thing here and one thing here next to each other. And so, like I was just saying, so we have to define the system and the surroundings. And so what we mean by that, we'll do this, right? I'm going to call this the system, and we're just going to use pictures at first before talking about any chemical reactions and any, molecules and all that. So this will be called the system, right? Which in our case for chemistry is the chemical reaction. Okay. And then we're going to define the whole, right, everything that's surrounding the system, we call the surroundings. Right. So the surroundings can be the solvent that the chemical reaction is taking place in. It can be the air, right? Or it can be the container that the chemical reaction is taking place in. It can be the air around the container. In reality, there's no limit to what we call the surroundings, right? Because you can go out further and further and further, right? And it'll always be the surroundings of what is surrounding the chemical reaction. But in practice, the most important, areas that are surrounding the system would be, like we said, the solvent, which we can measure the temperature of, the container, right? The air around the chemical reaction. And so, what happens, right? We were talking about potential energy being stored in the bonds of a chemical, or in the bonds of molecules. And so what happens is when those molecules in the system in a chemical reaction, right, when their potential energy leaves the system and gets transferred into kinetic energy, then what happens? Does the kinetic energy of the system decrease or increase? Does the kinetic energy of the system decrease or increase? Does the kinetic energy of the system decrease or increase? And am I saying system or surroundings? Does the kinetic energy of the system decrease or increase? Good, I think I saw some changed answers. That's good. Right? Yeah, yeah. So what happens, right, is the potential energy of the bonds in the chemical reaction, right, can get transferred to kinetic energy that leaves the system. And so that means then that the surroundings, right, so we can say that the potential energy turns into kinetic energy in the surroundings. And so will the surroundings feel hot or cold? Will the container, will the air around the system, the surroundings, will the surroundings feel hot or cold if potential or if kinetic energy is increasing in the surroundings? Right? Will the surroundings feel hot or cold? Good. Yeah, the surroundings will feel hot. And so just to, just lukewarm. All right, and then so to just spell it out here, right, what was happening in this case was that the potential energy, right, is being released into the surroundings as kinetic energy, because as we just saw, right, potential energy can transfer into kinetic energy. So the overall energy of the system doesn't, like, there's no, right, energy cannot be created or destroyed during a chemical reaction. That's a law of thermodynamics. And so it just gets transferred from potential to kinetic energy, just like we were talking about the ball rolling down the hill, right, or food being transferred into kinetic energy. So that's what's going on here. Potential energy transfers to kinetic energy from system to surroundings. So let me actually make a change here, pardon me. So potential energy from system transfers to kinetic energy in surroundings. Okay, and the reason I'm showing, so this is just one, this is like an example of what can happen, right, during a chemical reaction. Sometimes potential energy that gets transferred to kinetic energy, which leaves the system, right, into the surroundings, and the surroundings feel hot. Right. There is another instance where the reverse can happen. Okay, this is one option for the energy transfer in a chemical reaction. There's another option that happens during chemical reactions. And when I say option, I don't mean that it's like, oh, the reaction just decides which one to do, right? It actually has to do with the type of bonds in the reactants and the types of bonds in the products, which we'll talk about a little bit more in a second. But it all has to do with the type of bonds in the reactants and the products. So here again is our system. But this time we're going to show the flow right, of kinetic energy from the surroundings, right, being transferred into potential energy in the system. So this time, kinetic energy comes from the surroundings and gets stored as potential energy in the system. That kinetic energy is coming from the surroundings. So, do the surroundings feel hot or cold? Kinetic energy is coming from the surroundings. Right. So if you touch, the container, right, that the chemical reaction is occurring in, right, does your hand, do you feel cold? Like, does it feel cold or hot? And you're all saying cold, and that's true, right? Because kinetic energy has to come from somewhere. So say I'm touching, like I'm the surroundings here, kinetic energy is flowing from the surroundings into the system, the chemical reaction, then that means kinetic energy is coming out of my hand, right? Heat is being transferred, therefore, into the system, and that energy is being stored as potential energy in the bonds of the products, which we'll talk about in a second, too. So in this case, kinetic energy from the surroundings transfers to potential energy stored in system. Okay, and so kinetic energy turns into potential energy. In the system. And like you all told me, then the surroundings will feel cold. Right? Including your hand, your body will be the surroundings, right? So air, body. For another example, another like piece of the surroundings that we can think of. Question: does everything want to have kinetic energy? Like it wants to receive transferred energy from things that already have it? Well, I would say that it's not that it wants to, right? It's just that that's the way that it goes. Like, think of, I would say, it's kind of automatic the way that it happens, right? So like, if something has a more molecular motion, right, more vibration, right, then that vibration has to go somewhere. And if it can be transferred into another object with less kinetic energy, it's going to flow that way. In the universe, at least as far as we know, right, that is the natural flow of kinetic energy from high to low, not the other way around. So I wouldn't say that it like wants to, but I would say that that's the way that it naturally occurs, from high kinetic energy being transferred into an object with less kinetic energy. So yeah, does that make sense? Oh, JJ, I didn't see your question. Yeah, thank you for bringing me to the point, exactly. So in this case, is heat going out or coming in? Right, right? Heat is going out, right, into the surroundings from the system, right, out from the system. And so that means then that the word we use to describe this process, like you said, is exothermic. Right? So exo, right, means out. Therm means heat. Right? So heat out for exothermic. That's the way that we describe this process here. Yep, good. And this one over here is called what we use for when heat is going into, right? You got it. Endo. Endo, right, means into. Therm, again, heat. So heat going in, kinetic energy coming from outside the surroundings into the system, being then stored as potential energy in the system. Other questions? Yeah. An example of endothermic, I'm going to show 2 demos, which you'll see. But can you all tell me, do you have examples of an endothermic process that you're thinking of? Like taking a cold shower? It depends. We have to, okay, so here comes the part where we have to think about defining the system and the surroundings. So if you take a cold shower, are you this, so should we define you as a system? Like okay, so let's define you as the system if you're taking a cold shower. If you're taking a cold shower, is heat leaving you and going into the water? Or is like it the opposite? Is like heat leaving the water and going into you? Hold on, let's stick with, hold on. So let's stick with the like taking a cold shower. You're the system. So is heat leaving you or going into you? Right. Hold on, let's think. Okay, so Maddie. Okay, so let's think. So leaving the water and entering it. So let's clear this up. Let's make sure. Okay, so remember that kinetic energy only flows from high to low, right? So if you're taking a cold shower, right, the way that it's cooling you is by taking heat out of you into the water. So the water is colder, right? The water has low kinetic energy. You have high kinetic energy. So it's leaving, the heat is leaving you and in effect heating the water, right? So if you took the temperature of the water before touching your body and after, the temperature of the water would be higher because it took kinetic energy out from you to heat the water. Is that okay? Yep, from you to water, yep. Cold shower, yeah, cold shower. Exactly. In a hot shower, it's the opposite, right? That's keyword, yeah, cold shower. Right. And then other people were thinking things. Where is the heat going through? Let's see. Boiling water in the pot. Right. For boiling water in the pot, right, it's the opposite, right? It'd be like taking a hot shower, right? The heat is coming from the heating element into the water. So the system is then, so endothermic, right? Okay, so wait, so were you, so let's like label the cold shower thing, like are you, is the body, is the system endothermic or exothermic? If we're talking about taking a cold shower and you're the system. Right? Back to the cold shower example, the system is the body. So is it endothermic or exothermic system? Yeah, so I'm getting a mix, but most are saying exothermic, and that's true. So again, that's a good one. I like that one because it seems like, right, it seems like, oh, the surroundings are cold, it must be endothermic. But again, where is the heat flowing from and to? It's flowing from your body out to the water. So it must be going out like this and exothermic. So taking a cold shower, if you are the system, is exothermic. Yeah. Okay. So then boiling water in a pot, if the water in the pot is the system, is that endothermic or exothermic? Boiling water in a pot, the water is the system. Right. Endo or exo. Yeah, exactly. So do you see why, and then on the reverse, right? For the water in the cold shower, right? Is the water gaining kinetic energy or losing it? right? The water in a cold shower. So it all depends, right, on what you define as the system and the surroundings. Right, the water would be gaining. So the water in the cold shower is endothermic, right? You in the cold shower are exothermic. So yeah, so defining the system and the surroundings is so important, and that's why I wanted to start with that. You know, it all depends on your point of view. So defining the system is important. So combustion, okay, we'll talk about that. Yeah, so we're gonna talk about combustion in a second. So I've got some demonstrations. We're gonna try to do this on the screen here, okay? All right, so you tell me which is endothermic and exothermic. So we'll start with this one. Okay, so I've got here a mixture, or rather not a mixture yet, excuse me, two pure substances. They're both crystalline, right, ionic compounds, and we'll talk about the actual chemical reaction up on the board in a second. But, and what's gonna happen is I'm gonna mix them together, and I've also got this plank here. So onto this plank, I am going to place a little bit of just DI water. And I'm going to place the big beaker onto the plank with the DI water and mix the contents together into that big beaker. I know you can't quite see, but I'll show you in a second. Okay, and so I'll hold this on here. You can see me over there, right? Okay, so I'm gonna hold this on here and mix the contents. And we can start to see in a second. Whew. And I'm getting very strong ammonia fumes right now. Ammonia is one of the products, so we know it's working. And do we start to see it? Can you see it getting a little like pasty? Right? It's kind of sticking to the sides. And so what we're seeing is it kind of starting to turn into a slurry, it's called, where you've got a lot of solid kind of interspersed, right, mixed in with a liquid. And so it's actually turning kind of liquidy. What's happening is water is actually being liberated from this reaction, and we're going to write it up on the board in a second. And what happened? What happened? Oh my gosh. Yeah, it froze. Okay, so exactly. So what's going on? Science is the coolest. Yeah, for sure. Chemical reaction, that's true. Yep. A change in phase is also an indication of a chemical reaction sometimes. Like we see water being liberated here. Most of the time the phase change is just chemical physical, but in this case we see a phase change and it's chemical. Yeah, so is this, so, okay, so let's define the system as the contents that I just stirred together. Okay, so let's define the system. We're in chemistry, so we're defining the system as the chemical reaction. Okay, so the chemicals, right, are reacting inside this beaker here. So in terms of the system, inside that beaker, right, was this an endothermic reaction or an exothermic reaction? Right. The water froze, right? So think about what's up on the board, right? Exactly. Good. So is it like this, right? Did kinetic energy come from the surroundings and go into the system and the surroundings feel cold, right? Or did potential energy get transferred to kinetic energy and move out to the surroundings and the surroundings feel hot? The water froze. Yeah, exactly. Right, it's definitely not hot, right? The surrounding, this is very cold. Like I'm feeling this, I can't even like get that off of there. Okay, so the water froze, right? Even underneath the plank, it's cold under there. I can feel it, colder than the sides. I've never noticed that before, that's kind of cool. Right, so right here underneath the plank is cooler than over here, right? So it's actually removing the kinetic energy from the plank, from the water. It froze the water, it stole, like someone just said, right? It took the kinetic energy, right, from the water into the system in order for the chemical reaction to occur. Right. Yep, exactly. Kinetic energy came from the surroundings and turned into potential energy in the system. So now that system actually contains like an elevated potential energy. There's actually energy stored in that system now. Okay, good. Let's do another one. See the balloon over there? Haha, all right, let's do this. So you tell me which one this is, right? Is this one endothermic or exothermic? First, I will light the meeker burner. This one is called a meeker burner, bigger than a Bunsen. Same idea. So I'm going to turn on the gas, which is pure methane. So the Bunsen burner is lit. And is that exothermic or endothermic? The combustion reaction that's occurring, is that? Oh, it's so lovely there. Here in the room, yeah, it's lovely. Is that endothermic or exothermic? The meeker burner? Yeah, right? Because I can feel it, right? It's hot. Like me being the surroundings, right? What's happening is the air, right, is the surroundings. The air is getting kinetic energy transferred into it. And then that air that I'm feeling is transferring its kinetic energy into me, right? It'll expand, you know, infinitely, but again, the most important surroundings are the ones that can actually, like, you know, that are actually, you know, what should I say, like, more immediate, you know, more immediate surroundings are more important than, like, you know, the rest of the world or whatever, but it could technically be still surroundings if we're talking about the whole Earth. All right. Okay, be careful if you have headphones in right now. I would probably like consider removing them, right? Because I do have the balloon. Just be careful. What did I say? Did I say immediate? What did I say? Immediate surroundings. All right. Okay, everyone, okay, be careful. If you have headphones, I don't know what this will sound like in your speaker. Okay, tell me if this is endothermic or exothermic. And the beaker burner stayed alive. Endo or exo? That's right. Cool, well, I'll get to see it on the recording. I'm not gonna do another one, but we'll do another one again. I can't even get this plank off of there. I'm gonna put it in the hood because the ammonia is too much. Okay, so now we're going to write up on the board. Everyone okay? Can I do that? Okay. Let's start here. Okay. So we can represent this. So those were the macroscopic representations, right? So we can also represent that in symbols, right? Using letters and numbers in a chemical equation. So we're going to start with the exothermic one, just like we started here with exothermic with the diagram. And so we can draw an energy diagram. Okay, which shows, and what I'm going to do is draw in blue to highlight the fact that what we're going to be drawing here is the system, which we just showed over there. I wrote in blue. So I'm going to write in blue to show you the energy diagram involved for the combustion of the propane, which was in the balloon over there. Okay, and so on the y-axis, we will place energy, and on the x-axis, we'll place reaction progress. Okay, and okay, it looks like for this class, so what I'm actually going to do, I'm not going to show propane because I kind of want to draw it out for people. And it would take, hold on a second. Okay, so yeah, we're going to show the reactants at this energy level here, right? These are the reactants. And in the balloon that we just exploded, those reactants were propane, so C3H8. And the other reactant for any combustion is what? That was propane. Yeah, oxygen, right? O2, right? And so it was the propane and the oxygen as the reactants that reacted to form carbon dioxide and water. And so if we are going to draw on our energy diagram, so this is right here, this is the level of energy of the reactants. I just chose arbitrarily where to place that on the energy diagram. If we're going to draw the energy level of these products here, is that energy level, and this is potential energy, we should say potential energy here, is the potential energy of the products lower or higher, right? Am I going to draw the potential energy over here or up here for the products? Let's not balance the equation right now. Will the potential energy, and Nayeli, I don't know what, if you can't see the whole screen, maybe can you expand? Okay. So yeah, the question is, will the energy level of the products be lower or higher? Right? And this is the exothermic, right? So remember, for exothermic, did the potential energy get transferred to kinetic energy going out? Or did the system gain potential energy and come in? Right? This is the system here. So for the exothermic process, right, this is the system. We said that potential energy goes out as kinetic energy to the surroundings, right? And so if potential energy is moving out to the surroundings, that means will the energy level of the products in that system be lower in potential energy or higher in potential energy? Will the energy of the products be lower because potential energy went out, or will it be higher as potential energy goes out? Yeah, good. So I'm seeing a lot of lower, and it's true. So that means then, right, in this exothermic energy diagram, we see a decrease of potential energy going from reactants with a higher potential energy, right? And remember that potential energy is stored in the bonds, right? And that means when the products, when they decrease, right, in potential energy, the energy that was stored in the bonds leaves and gets transferred to kinetic energy, leaving the system. Yeah, let's balance the equation. Can you all balance this equation here? I'm going to get started on the other side. Balance that equation. Name this tune. Balance this equation. By the way, this was propane balloon explosion. For endothermic, we're going to talk about the frozen plank. All right, cool. So this one was one of your homework, right? Balancing the equation for the combustion of propane. And Nayeli, how are you? Did you get the whole screen? Okay, good. Okay, so we can balance nonmetals first. The only nonmetal that's not carbon or hydrogen in this case is carbon, right? So we've got 3 carbons on the reactant side. We've only got 1 over here, so we can put a 3 here, right? And then we can balance hydrogens. And so when we do it in this order, especially for combustion reactions, it's a lot simpler to balance, right? So if we do hydrogen first, you've got 8 over on the reactant side. And we've got only 2 over here, so we can place a 4 in front of the water. And then oxygen is alone for combustion equations. And so that means that when we save oxygen for last, it's easier. So 4 oxygen plus 3 times 2, 6, right? So 6 plus 4 is 10 oxygens. So what do we put in front of the O over here? Yeah, a 5. 5 times 2 is 10 oxygen. So that's the balanced equation for the propane balloon combustion. And so when we think of combusting a propane balloon or any combustion, right, we can think of the reactants as higher in energy than the products. And let's write this out here, right? Energy released to surroundings. A bird is knocking at the door. Means that is called exothermic. Right? And then we can say down here that the products, right, have less potential energy than the reactants. And so which bonds are stronger? Which are more stable in an exothermic equation? Which are more stable? Is it the products, right? Are the bonds in the products stronger and more stable? Or are the bonds in the reactants stronger and more stable? Which is more stable? Think of it this way, right? The way I think of it is, which is more stable, when you are lying on the couch and relaxing with low energy, or when you're high energy running around getting errands done? Which is more stable, on the couch or running around? Right? So on the couch, yeah, you're more stable when you're relaxing, low energy on the couch, right? Than you are when you're high energy and hyper and trying to get everything done, right? And so that means then low energy is more stable. Lower energy is more stable. So that means then that the products of an exothermic reaction, since they are lower in potential energy, they are more stable. So the bonds in the products are more stable than the bonds in the reactants for exothermic. And this also tells us that they're stronger. So the stronger the chemical bonds, right? The stronger the chemical bonds, the less they're able to like move, right? The less the atoms are able to move about each other, the more like rigid they are. So the stronger the chemical bonds, the more stable, because they're not as like loose and able to flow around. Okay, so the stronger bonds are more stable. So that means then the more stable, right? The lower the energy. So let's see, let me make this connection here real quick. Just like we were connecting this to being on the couch, it's more stable when you're relaxing, right? With lower energy. And so more stable means lower potential energy. So stronger the bonds, the more stable those molecules are, the more stable the bonds are, and the lower the potential energy. Just like if I have any object suspended up high, right, that's less stable than after it drops and falls to the ground, right? So lower potential energy on the ground, more stable. Lower potential energy in the products of an exothermic reaction, more stable. Good. I wish I were stable on my couch right now. All right. What questions do you have? We're going to wrap it up. What questions do you have? Does this make sense? Does that help like with the couch analogy? You're welcome. Very happy that it worked. Okay, okay. Yeah, energy I find too that it can be daunting. Like every time I stress about giving this lecture because I want it to make sense and I'm scared that it's not going to. And but then once you get into it, it's not that bad. It's one of those things. I've always felt that way too. That like it seems really scary. There's lots of new vocabulary and everything, but once you get into it and take it step by step, it's not that bad. Okay. Hey, admin, is that Matt? All right, you're welcome. I'm so happy. Okay, so if you don't have me for lab, I believe that Sarah is going to be here, but you're welcome to come in to lab. That's fine. So then, oh, good. I'm glad it made more sense than your high school. But if you don't have me for lab, that's okay. So what we're going to do, I'm going to stop the recording. Okay. Okay. Good. 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 Yeah. More stable, lower energy on the couch. Okay. And so then I'm gonna come back in 10 minutes and what we'll do is start a new recording, but it's the same link, it's the same thing, so you can just come on back into this meeting in 10 minutes, okay? Yeah, homework, yeah, lab today is just review for the exam, so that means then that you can come back and just ask questions and we'll go over things. I can show you some things on the screen. So you're just asking me questions that you have for the exam review. And yeah, don't worry about homework. We'll just collect it. I'll collect it next time we see each other. That's fine. Willow's lab. Yeah, you can come to my lab. That's fine. Yeah, I'll just see you here. And we start in 10 minutes, okay? Wednesday's lab is not in person. No, Wednesday's lab is not in person. We're going to be on Zoom too. But like I said in the email, the lab on Wednesday, I'm just going to be here for you, question and answer. I'm not going to start the lab. Like, I'm hoping that we can come back to class in a couple of weeks and we'll see how it goes then. But yeah. Okay, cook some food during the exam review. Sarah does have her own link, okay? So like you can either come to mine in 10 minutes or then. No, you don't come to lab Wednesday, but you are like this. We can't cancel lab, but what I'm going to do is just be available for you. Okay, so you don't come to lab, but you have lab on Zoom. Exactly. For my lab. I don't know about your instructor, but I know Sarah and I, yeah, are going to be available for you. Not instead. I don't know if Sarah wants everyone. So you're welcome to come to my lab. In 10 minutes, I'm going to start a new recording. But I don't know if that's like sufficient for what Sarah wants you to do. I don't know about instead. So I've got a list of everyone who's been here on the participants today. So I'm going to be taking that like screenshots of that pretty much and filling it in for participation. Okay, so see you in 10 minutes. Okay, bye.